For my midterm assignment, the reaction I did was the UG multi-component reaction. The UGI multi-component reaction is a reaction that can be run in the lab safely and easily, as long as all precautions are taken, as we will later discuss. It is inexpensive and readily available due to the fact that the reagents and solvents used in this preparation are commercially available and used without further purification. It has been observed that UGI products sometimes precipitate in pure form from the reaction mixture. Because of this, the reaction can then be easily scaled up without requiring costly purification procedures such as chromatography. For the checking process, the checkers did make some comments regarding to certain parts of the reaction. For example, when the submitters were running a cooling bath of 275 grams of ice and 150 grams of ethanol to approximately get -10 degrees Celsius, the checkers used a thermocouple in the ice and ethanol bath to accurately measure this temperature for the duration of the reaction. Another comment they made was when the submitters were running a column chromatography, the checkers found that ethyl acetate was difficult to remove. Placing the purified reddish-brown oil under high vacuum for 12 hours was required to remove the ethyl acetate. The apparatus that was used in this lab was a 500 milliliter 3-necked round-bottom flask equipped with a 6 cm Teflon blade overhead stirrer, a 60 milliliter pressure equalizing dropping funnel holding a nitrogen inlet and a thermocouple. The Teflon blade overhead stirrer was purchased from Aero Engineering Mixing Products model. The reagents and starting materials were trifosgene 98% and amino acetaldehyde dimethyl 99% from AK Scientific Inc. N-phenylethyl formamide 97%, trimethylamine 99%, paraformaldehyde 95%, and cyclohexane carboxylic acid 98% from Sigma Aldrich. For the reaction procedure, into our apparatus, a mixture of N-phenylethyl and trimethylene in dichloromethane was added into the flask, and the solution was cooled to approximately -10 degrees Celsius using an ethanol ice bath. Trifosgene in dichloromethane is added dropwise to the stirring mixture via the dropping funnel over a period of 45 minutes, resulting in a dark red-brown solution which can be seen in the middle picture. The reaction mixture is stirred at -10 degrees Celsius for an additional 30 minutes. In a separate 50 milliliter round-bottom flask, which is charged with a mixture of amino acetaldehyde dimethylacetol and paraformaldehyde in 50 milliliters of methyl, is equipped with an air condenser and heated to 80 degrees Celsius in an oil bath with stirring until a clear solution developed. After allowing the solution to cool to room temperature, cyclohexane carboxylic acid is added. The resulting solution is then added together with another 50 milliliters of methanol to the in situ formed isonide reaction mixture. The reaction mixture is left to warm to room temperature. The overhead mechanical stirrer and 60 milliliter pressure equalizing dropping funnel are replaced with red septa and a 2.5 centimeter Teflon stir bride. For the reaction workup, after stirred at room temperature for 48 hours, the reaction mixture is transferred to a 1000 milliliter 1-necked round bottom flask, along with CH2Cl2 that is used to rinse the flask, and the solution is concentrated by rotary evaporation to remove the methanol. Then the mixture is redissolved in another 50 milliliters of CH2Cl2 and transferred to a 250 milliliter separatory funnel, which is washed with 350 milliliters of water and 350 milliliters of saturated NaHCl3 and dried over MgSO4. The drying agent is removed via filtration through a medium porosity 150 milliliter filter funnel, and the resulting solution is collected into a 1000 milliliter round bottom flask in which the solution is concentrated by rotary evaporation. The red-brown oil is purified by flash chromatography on silica using hexanes and ethyl acetate as the eluent. The collected fractions are placed in a 1000 milliliter round bottom flask and then concentrated by rotary evaporation to yield a reddish-brown oil, as seen in the middle picture, which is then placed under high vacuum for 12 hours to get 7.46 grams of our product as a brown solid, as seen on the right picture. In order to test the purity of our product, an NMR was run, and from these pictures that were submitted by the submitters, you can see the products. And for the hazard warnings, the procedures in organic synthesis are intended for the use of persons with proper training in experimental organic chemistry. All hazardous materials should be handled using the standard procedures for working with chemicals. The most dangerous part about this reaction is working with triphosgene, which is a less hazardous substitute for the highly toxic gaseous phosgene. However, this should still be handled very carefully, as triphosgene may be fatal if inhaled and causes burns by all exposure routes. This water-reactive substance liberates toxic gas upon exposure to water. Triphosgene is a lacrimator and can decompose violently at elevated temperatures. Triphosgene should always be weighed out, and the reaction should be performed in a well-ventilated fume hood. For our discussion, on the right you can see the mechanism that was used in this reaction. You can see how the curved arrows show the electrons moving and how they attach to each other to get our final product. The UGI multi-component reaction is gaining increasing attention, but what is its importance? In recent work, it's been able to generate the isonitrile in situ, which is making the UGI reactive even more attractive. While several approaches towards aminoacrylamides are possible, the UG approach is faster and moreover impressive by a very large substrate scope. A little bit about the authors is Alexander Dumling studied chemistry and biology at the Technical University of Munich. After performing his PhD under the supervision of Ivar Gugi, he spent his postdoctoral year at the Scripps Research Institute in the group of Barry Sharpless under a prestigious Fedor Leinen Research Fellowship from the Alexander von Humboldt Society. He is also a founder of several biotech companies. In the middle, she received her undergraduate chemistry degree at Nanjing University in 2002. She then moved to Shanghai, China to pursue her doctoral studies with Dr. Zhu Zhongyao at the Shanghai Institute of Organic Chemistry. She is now working on synthesis of ghrelin O-acetyltransferase inhibitors. Andrei Boltix received his bachelor's degree in 2007 from Han's University and started working at the University of Groningen, in which in 2011 he joined Dumling's group as a technician. Emma L. Baker Tripp received her bachelor's in chemistry from Grinnell College in 2013. She is currently pursuing her PhD in organic chemistry in the laboratory of Professor Neil K. Garth at the University of California. And lastly, we have Ping Cao, which received her bachelor's degree in 2002 from Fudan University, China. After 5 years of studies, she obtained her PhD in organic chem from Shanghai Institute of Organic Chemistry.